Hi, hello. Welcome to section number 6. Unfortunate news. I am sick. So yet again, I'm not delivering on my section notes. Ugh. I feel like I'm part of a meme where it's like when the semester like beats you down and like it's going to come to section 10 and I'll fully be dead. Like I won't be here. But no, I am committed at least for section 6 to going and making the nice section notes and everything. I have a draft today that I'm going to work off of that's a little bit the version I've used like in the past, and I've added some of the stuff from this class. Some of it I'm just going to like handwrite out, so thanks for bearing with me. But I have my like large tea and box of tissues, so we are really out here. Yes. So again, apologies that there's not a nice section document. Um, but game plan for today, so we're going to be talking about the Lecture 6 content, which is a little bit shorter, Lecture 6. We're still probably going to use the whole time because the reactions in Lecture 6 are rather long. But yeah, it's just an interesting, different kind of pacing from the summer version. So like, for example, for y'all, all of lectures 4, 5, and 6 in E-17 was crammed into 2 lectures for the summer. It was all just lectures 4 and 5. So a lot of it's just kind of expanding it out and everything. But general game plan, we're going to start off talking about acetals. Then we're going to go into amines and enamines. And then we'll spend a little bit of time on protecting groups and reductive amination as some kind of like final topics. But that's the game plan. Any kind of like logistical questions before we jump into things, or anything people are like especially confused on or want to talk about? I also have my very strong cough drops, so we are out here.
Oh, and I'll say one quick. I
Yep.
was gonna stay for office hours too, but
Mm-hmm.
when I'm just making my chart on all the different, like the reactant, reagents,
Mm-hmm.
products, I was kind of confused on amine formation. So I'm sure it'll be answered here, but I just might have some specific questions. I was struggling to kind of get that pattern down for
Yeah.
those reactions.
Yeah, totally. Especially now that we have multiple ways to make amines. We started off with only 2 ways of making amines, of reducing a nitrile or reducing an amide. And now, after today, we have 2 more ways. So we'll definitely be talking about that when we get to this like 5th section, the reductive amination. Work. Okay. Well, to start off, I wanted to spend a little time with the acetal reaction. So this scheme might look a little bit familiar. This is kind of what we were doing in lecture, I think, or section 4, I guess it was, the first one where y'all learned reactions, where we did this kind of analysis of it for hemiacetal formation. And hemiacetal formation, compared to the lecture 6 reactions, cute, sweet, quaint. It's short, it's like 3 steps. But now we're in these acetal and enamine reactions. They are much longer. They're more like 6 steps. And so I think it's really easy for these to get really lost in the sauce. So one thing I thought might be helpful is just doing a reaction analysis on it to kind of get an idea of the reaction substeps and what's going on. So first off, overall, just analyzing our line reaction, the acetal formation reaction goes from a ketone or aldehyde, and it turns it into an acetal, and that's also or a ketal, which we don't really do a ton of distinguishing between. We can typically just call like them all acetals. Ketone or aldehyde. The other thing that we have to have is an alcohol, and typically we're going to have 2 equivalents of it if we want to add 2 equivalents of it on our molecule. There are exceptions for some like diols, so you could have 2 alcohols on the same molecule like this, in which case you don't need 2 equivalents of it because there are 2 alcohols in the one molecule. And then you also need some source of acid. So for the conventions of our class, we don't write just H+, which is one of the edits I'm going to make to this. We write the like protonated version of the molecule. But let's see what this would look like. So, our main reaction goals that we need to try to accomplish, just looking at our line reaction. In goals, remember, for a chemical reaction, are bonds that you need to make and break. So here, we need to break, like fully break, our CO bond right here. So when we do that, we need to break our sigma CO and pi CO. And then we need to make two bonds between our carbon and our OET alcohol here. So, like, generally speaking, what's happening is our purpose of this reaction is to reversibly interconvert between the ketone or aldehyde functional group and the acetal. And our generalization is we would have some, like, aldehyde here. We'd have some alcohol and acid. And then we would form our acetal product with ORs added in its place. So, with this in mind, let's analyze the reaction. So our first step, and I'll write it out for our class, we write out the specific species here. So we're going to have the protonated version of our alcohol. And our first step is we protonate the carbonyl. And the purpose is to lower the energy of the LUMO, that pi star CO, to make it a better electrophile. Second step, we have an alcohol nucleophile attacks a carbonyl electrophile. And these are the exact same steps that we saw for hemiacetal formation as well. So when we are doing this, this step accomplishes a couple of our goals. So we broke the pi CO and we made one of our OET bonds onto that central carbon. Okay, so once we attack and break our pi, then we have a tetrahedral intermediate, the apartment with 4 roommates. And looking ahead, eventually what we need to do is we need to do a lone pair push from this OET and kick out water. And if we trace this oxygen here, this oxygen that's in this water in this step, it used to be this OH. And this OH, oxygen, came from our carbonyl. So one kind of distinct feature here for these reactions in lecture 6 is at some point in the reaction, we are going to fully kick off a water. That's the main one that we see here. So how do we get from this to this lone pair push cinematic moment where we're kicking off water? Well, right now, this OET is positively charged, and so it's not very good at doing a lone pair push. It doesn't want to give up even more of its electrons. And so the first thing that we do is we are deprotonating in order to make this neutral. And then here we are at a hemiacetal. So for the hemiacetal reaction, this is where we stopped. But here, if we are an acid and we have enough of our alcohol, then it'll go on to react. And going from this neutral intermediate of the hemiacetal to the one where the lone pair push happens, the big thing is we are trying to make this O a better leaving group. Because right now, if we were just to try to do our lone pair push from here, we would be kicking off OH minus. And one kind of warning here is you never want to be kicking off something with a negative charge when you are an acid. It is just not kinetically going to happen here in terms of kicking off something with a negative charge. So in acid, you are only going to be kicking off things that are either positively charged or neutral. Whereas in base, you're never going to kick off something that's positively charged. You're only going to kick off things that are neutral or negative. And so that's kind of one trend to watch out for. So what we're doing in this step is we are protonating the OH to make it a better leaving group. And these two steps together we can group together and we can call it a proton transfer. And our way of abbreviating it is we can just do an arrow between this starting molecule and this bottom one, which I'll write out a little bit clearer here. And you can just write PT on the arrow, and then you don't have to draw all the curved arrows. Also, just to be super consistent for our class, I'm going to draw out the versions of this that you are more used to seeing. So you would see a lone pair on HOET go and do the deprotonation, and then you would have H on the protonated version of the alcohol over here. I forgot to draw that arrow in the first one. Okay, so our protonation and proton transfer here. Our purpose is to make the OET neutral for the lone pair push, and then it's to make OH a better leaving group for the lone pair push. So all of this step 3 here, these two steps together, is set up for the lone pair push. It's the rising action in our story, so that we can get to step 4, the lone pair push off water. And when we do this, we are accomplishing another one of our chemical goals. We are breaking the sigma CO bond that was in our original carbonyl. So we are fully severing off this bond and kicking off water. So once we're here, if we look at our chemical goals, like I might try to highlight some of these. So the breaking of bonds, we've already done. We broke the pi, we broke the sigma, and then we've done one of our making our OETs on. So the 5th step here is just accomplishing the rest of our chemical goal. So we are going to have an alcohol nucleophile attack a carbonyl electrophile, the exact same thing that we saw before. So I'm going to just copy and paste because it's exactly the same. And then the reason for it is because it accomplishes one of our chemical goals. It makes one of these OET bonds. So that finally, the last thing that we have to do is we just need to deprotonate our molecule. So I'll write this out as a lone pair on the HOET is going to go and grab the hydrogen off. And the reason for this is to neutralize the molecule. And suddenly we are at our acetal. Maybe I'll also just point out this hemiacetal intermediate. So again, the reason why I go through this with y'all is not to be like super pedantic about it, but to just be like, if we're not thinking about why each step is happening, it's really just a mindless memorization game, and like there's only so much that we can do. Like this should be very much like an active thinking process to engage with it. And so our reaction summary, we won, protonate the carbonyl. We too have our alcohol nucleophile attacking a carbonyl electrophile. 3, we did a proton transfer. 4, we did a lone pair push off of water. And then 5, we did another alcohol nucleophile attacking a carbonyl electrophile. And last step, and I'll make it small so it all fits, we did deprotonation. So seeing all these steps together, we still only used 3 different types of mechanistic logic. We had acid-base steps, so protonation, proton transfer, deprotonation. We had alcohol nucleophiles attacking carbonyl electrophiles, or nucleophile attacking carbonyl electrophile. And the last type that we had is a lone pair push, kicking off some leaving group, in this case water. So, with this in mind, let's go ahead and look at the first practice. I have some other things I want to do here with the acetal reaction, but I think it would be good to go ahead and see this in practice.
Colton, can I ask a question really quick?
Please.
Thanks. So, is the point of step one, and we're under acidic conditions,
Mm-hmm.
right?
Mm-hmm.
So, is it correct to say that you protonate to activate that carbonyl to both lower the energy of the LUMO, which makes it a better electrophile, and it also like improves
The reactivity?
like okay, yeah, that sounds
Yeah,
good.
no, like snaps. That was beautiful. That's exactly
Okay.
what it is.
So that allows like the nucleophile, it's like a better environment for it to attack. Is that
Yeah, because like an
okay?
alcohol on its own, kind of a crappy nucleophile. Like an alcohol is basically like water in terms of reactivity. And do we think of water as a very reactive compound? No. And so, if we are going to have a crappy nucleophile, we need an acid present in order to make our electrophile better. And it's why like the opposite strategy happens in base. In base, we make our nucleophile better, and so we can have a okay electrophile of just a plain Jane carbonyl. So either way, acid or base, we are lowering that homo-lumo gap between our like lumo and homo. In acid, we lower the energy of the lumo, and in base, we raise the energy of the homo.
Thank you.
Yeah, totally. So over here, let's look at this. So there is a lot going on here. First, whenever we see a reaction, we analyze functional groups. So what functional groups do we have in this starting material?
Alcohols?
We just have alcohols, yeah. We have 3 of them. Then we have a ketone up here. And then what about in our product? We also have acid as a catalyst. So we still have 1 alcohol in our product. And then what's going on up here? She looks angry. Looks kind of like a little TV with antenna. Acetal, great. And if we were really being pedantic, it's a ketal, but I'm just going to call it an acetal. This is the thing. I don't even like telling students about ketals because I find it so annoying. So, like, normally when I teach it, I just say, it's an acetal. Like, there's no such thing as a ketal. They can't harm you. But here, because it's from a ketone, it would be technically a ketal. Great. Now, another thing I'm noticing is some stereochemistry things. So we see this plus minus, which indicates that we have a racemic mixture here. Okay, that's interesting. Well, do we have any stereochemistry in our starting material? Are any of these carbons stereocenters? Maybe that's a first question. Are any of these carbons attached to 4 different things?
Not at first sight.
Say one more time.
I don't think so.
Would it make a difference if I put this on a wedge? So, y'all are all thinking about the right things, but be careful. I didn't ask whether or not the molecule was chiral. I asked, is there a stereocenter? Is there a carbon attached to 4 different things? And actually, I'm so sorry, I led you astray. You're totally right. They're not 4 different things. There's a hydrogen, but these 2 are totally the same. You are 100% right there. So there is no stereocenter here. But somehow, in our product over here, we do have a stereocenter. It's attached to 4 different things. So we need to be on the lookout during our reaction for that to change. Something is going to change where this suddenly becomes a stereocenter. Okay. So now, with all this in mind, if we see a ketone and alcohol forming acetal, we should jump into the acetal reaction. So what's the first step of the acetal reaction? Well, we just said it's protonate the carbonyl. So I'm going to start out with a protonated version of my alcohol. And it doesn't matter which one of the alcohols you protonate, dealer's choice. And I'm going to have the lone pair on the carbonyl go and get protonated. So that's our step 1 protonation. Now that we have protonated it, we have made it a good electrophile. So now over here, we have for our second step, then alcohol nucleophile attacks the carbonyl electrophile. And for this alcohol, like, we could have any one of these attack. It does not matter which. So I, just for like the sake of argument, am going to have the far one go and attack. But any of them would work. Okay. So now, this is where it starts to get dicey. So we have an OH here, and this OH was from this OH over here. But now the other thing that's attached is this whole molecule. So we have the bond to the oxygen that attacked. That oxygen still has its hydrogen on it from over here. And then it's connected to the entire rest of the molecule. Now pause. Do we have a stereocenter? So first, is this a stereocenter? It's attached to 2 methyls, so not 4 different things. Okay. One of these other ones stereocenters now?
The second to last.
Yeah. But why? We didn't even react with this. Why is this now a stereocenter?
The group on the left and the group on the right are not the same.
Exactly. And that's why I was trying to set y'all up for earlier with my like questioning of this molecule. And you're totally right. Right here, there is no stereocenter because this OH and this OH are equal. But once one of the OHs goes and attacks the ketone, suddenly this thing is not equal to the other one. And so it's 4 different things. So in this step, because it could be either side that goes and attacks, we are going to get a mixture of stereoisomers. This is our first step where we get our plus minus. And because we have a stereocenter, we want to just pick arbitrarily one of the stereocenter versions to draw. We can pick either the R version or the S version, the OH being on a wedge or it being on a dash. And I was just showing this H here just for clarity to show the 4 different pieces on it. But the other thing I want to say is, like, this OH could have been on a wedge or a dash before. Like, just because we draw a wedge or a dash does not mean something has to be a stereocenter. I could have drawn it like this initially, and it would still not be a stereocenter. But now that we have a stereocenter, we do want to very specifically draw that wedge and dash. Now, I know that the stereochemistry on reactions like this is pretty tricky, so are there any questions related to this? Or anything that...
I have a question.
Please.
And Colton, I'm so sorry. I can't figure out how to raise my hand on Zoom anymore.
No, you're totally fine.
I don't know what happened. So, okay, with these stereocenters, so I understand how, like on our most recent part that we've drawn, that now there's a positive charge, the left is different from the right.
Yeah.
But where I get confused is I would say the right is similar to the middle, but I guess that's not true. So there's a carbon in between.
It's not even about like similarity. It's like literally this one carbon. One thing it's attached to is an OH. One thing it's attached to is an H. One is a CH2OH. And the other one is CH2OH carbon with an OH and 2 methyls. So it's about the exact identities. Like, I could make something really long and complicated where it's like, if I had the OH, H, I could have this like isopropyl looking branch thing. And like, this is still not a stereocenter because the 2 sides are exactly equal. But if I went and I added, or actually, sorry, that makes it exactly equal. But if I went and added like one carbon to one side, then it's suddenly a stereocenter because the left and right side are not exactly equal for these two in the plane. So it's all about the 4 different groups attached to that carbon directly.
Thank you.
Yeah. Okay, so now our step 3 of our reaction was a proton transfer. So what we are doing is, remember, we're trying to kick off this OH girl, and so we need to help pack her bags. And then the one who's going to be doing the kicking out is this one over here. So we need to make it a better leaving group. Or sorry, make it a better lone pair pusher. So we are going to do our proton transfer. And technically all of these are reversible. I tend to not write the reversible arrows on everything. And unless a question explicitly says that you have to indicate which steps are reversible and irreversible, you don't need to worry about it. But we can do our abbreviation here, where we protonate this OH2, and then we deprotonate the other side so it's neutral. And this is our step 3. Now, because I was grading some of the PSET for y'all this week, I want to just clear up some confusion. So the thing that is not true, the thing that is not happening on a proton transfer, is it's not that this OH is going and grabbing the hydrogen from this, like OH. It's not this intramolecular reaction. What this is code for, and I'll write out kind of the actual version over here, is we are first doing a deprotonation with like another molecule that's in the solvent. So we would have like another alcohol, and I'm just going to abbreviate it as HOR, come and deprotonate this. Making it neutral. And then we'd have a protonated alcohol come and protonate this. But those are separate interactions. Like the protonation, deprotonation are random other solvent molecules bumping in here and adding or removing a hydrogen. It's not going to be the same hydrogen moving from one to another. Yeah, that's kind of one mistake I saw with it. The other thing that I saw is like the order of this does matter. Like you 100% would want to deprotonate this before you protonate the other one. Why would we not want to protonate this first and then get an intermediate that has like this and this? Why is that not favorable?
I actually learned this afterwards after rewatching the session because it's basically because the molecule will have 2 positive charges and it'd be highly unfavorable.
Exactly. And it's highly unfavorable and just highly unlikely that the molecule is going to build up a 2+ overall charge. Really, it's more likely that it's going to move towards being neutral at all times. And so that is why we do first the deprotonation and then second the protonation. And with this abbreviation of the proton transfer, we essentially are letting you do that because these curved arrows should feel pretty like easy now. They should feel pretty natural to do a protonation and a deprotonation, and otherwise these reactions are super long. So enjoy the little abbreviation when you can. Okay, we are ready for our cinematic lone pair push. So here I'm going to push down from the alcohol, kick off water. This is step 4, our lone pair push. And what we're left with at this point is now, I ask you, is this a beautiful bond angle? No. I technically should like rotate it and do something like, okay, blah, 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 this. And actually I will, because that was way easier than I thought it was going to be. I think a lot of times me and y'all are intimidated by drawing things. But when it's easy to redraw it like this, I like to make the change. Otherwise, we typically are not grading you on your drawing of the bonds and the bond angles, unless we're in like a chair or something where it really matters. So now, our fifth step is another alcohol nucleophile attacks this carbonyl. And the question that we have to ask ourselves is we have two options for this. We can have this come and attack the carbonyl, or we can have this come and attack the carbonyl, this far one. So how do we know which one happens? Well, luckily we have the answer. Like, we have in our line reaction which one actually happens more often. And so we know that it's going to form a 5-membered ring, right? So what I'm going to do is I'm going to start counting at my carbonyl, because that's one of the things that's attacked. And I'm going to say 1, 2, 3, 4, 5. So if this oxygen that I labeled 5 goes and attacks, it makes a 5-membered ring. And that's what we see in our product. So that's what we want to happen. Alternatively, if we had this one come and attack, we'd make a 6-membered ring. And in terms of like why one is more favored than the other, to be so honest, I don't have an amazing answer for you. The thing I was going to say is sometimes 5-membered rings are more preferred than 6-membered rings, which sounds like a lot. But a lot of it, I think, has to do with like there being oxygens in this ring, and stuff that's like just a little bit beyond this class. So I don't have a good explanation for y'all on why, other than because the answer says that we formed a 5-membered ring. So we are going to have the lone pair in this oxygen come and attack, and we push up. And now, to help me out for step number 5, I'm going to just draw a 5-membered ring, and I'm going to make it look like the product, and then I'm going to like number things. So I see in my product, we have a 5-membered ring that looks like this. And I'm pretty sure that this is going to be carbon 1, because that's where we had 2 methyls attached to. And my numbering is totally arbitrary. It's just helped me keep track of everything. So if I do that, then I might make this 2, this 3, this 4, this 5. And that makes sense because 4 is the base of where we had the carbonyl. Also, this tiny little arrow up here, I think, is not cutting it, so I'm going to draw it a little bit bigger. And then on carbon 4, the other thing that we need to include is a CH2OH. So we have CH2OH. And then the last thing is when we went and attacked here, this oxygen that I labeled number 5, it still has its hydrogen on it. So remembering all those kind of peripheral bonds and things that were attached, that is what I typically refer to as like chemical housekeeping. Making sure you didn't just magic away an atom, or like, especially because you know where you're going, it's so easy to make the mistake of just drawing this and being like, oh, thank God, I'm done. And that will be like a -2 points, just because you're missing the last step, and it kind of magicked away a hydrogen. So in our last step, we have another equivalent of our alcohol. Coming and doing a deprotonation. And so from here, we get our standard product. So honestly, this reaction here is one where I think it looks really scary. But every single arrow that we drew in this process, verbatim, was the arrow in the standard mechanism. Like, there were no steps where we did something different. It was just straight up copying. And I was grading the like ester hydrolysis question in the problem set. And like that was one where people either got full points or they got like less than half points. And the people who got full points followed the curved arrows directly from the problem set. The only thing I think that's really kind of new and challenging here is the fact that we created a stereocenter during this reaction. That's kind of weird, quirky. Yeah, Jamie, What's up?
Yeah, Colin, I was just gonna ask, do we need to show the implied hydrogen on a dash when we finish out the question or okay, I bet.
No, 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 no. So if you have one thing written here, like if it's on a wedge, it's just automatically implied that the hydrogen is on a dash. If you had this on a dash, it would be automatically implied that the hydrogen's on a wedge. Because remember, we can imply all of the hydrogens in like a skeletal structure. The only time where you'd have to be sure to show a hydrogen is if we were doing kind of a more complicated representation where we drew all of them in the plane. So for something like this, if we had, we do have a hydrogen here on this molecule, but we would need to like tell the viewer, is this on a wedge or a dash? Because that is going to determine something about the structure of the molecule, and it's not obvious whether it's on a wedge or a dash. But if one thing is given on a wedge or a dash, the other one is obvious. It's just whatever the opposite is. Yeah, good question.
You think?
Yeah. Okay. So, this was kind of warm up. Sad to say. There are some hard mechanisms this section. So, part 2, she's a little wild and crazy. I mean, nevertheless, we are plucky, intrepid heroes, and we start off by doing the one thing we always know to do every time we see a reaction, which is do an analysis of the functional groups. So what functional groups do we have over here? It looks kind of funky. But we know that there are 2 hydrogens here. Yeah, it's an acetal. Remember, our only definition for being acetal is we have 2 OR groups attached to the same carbon. So that is 100% an acetal. Then over here, we have 2 alcohols. And then, what's this? It's another one that like looks really weird, but it's 2 OHs attached to the same carbon. And what did we call that? Where have we seen that before? So not quite. To be an acetal, you would need to have 2 ORs. Like you'd have to have carbons on the other side. But we did talk about a reaction from lecture 4 where we put 2 OHs here. So close. Not hemiacetal. Hemiacetal is 1 OH and 1 OR. There's another version for just 2 OHs. This was called, the hydrate. So weird. We definitely do not know a reaction that goes from acetal to like a hydrate, right? And specifically, we only know one reaction for this entire class that starts with an acetal, because acetals aren't that reactive. We only know how to take an acetal and like undo an acetal formation and turn it into a carbonyl in alcohols. So this is the, like when we clock that, hey, this is not a standard reaction that we know, but it's connected to something that we do know, this is where thinking at that line reaction level is really, really helpful. So you might remember, like we talked about doing a fake mechanism. And so like for the forward reaction of an acetal formation, the fake mechanism that I really like looks kind of like this. So I have like the reverse direction over here. Essentially, we need to erase a carbonyl. And then we need to, if this is our alcohol, that's ROH, we need to add 2 OR bonds to it. And the R is just whatever our R group is in the alcohol, in this case, ethanol. So I would say fake mechanism, 1 is erase carbonyl, and 2, add 2 ORs in its place. So we could try this out for this molecule. So, step 1, we are erasing the carbonyl. Okay. And then we have our alcohol, our kind of ROH over here. And our R group needs to be 3 carbons. So I'm going to put 2 ORs in its place. So I have my O's. And then my R group is 3 carbons, so a propyl. Bada bing, bada bang. We have an easy way of drawing what our product is. But now, we also want to be able to work in the other direction. We want to figure out, okay, if we have an acetal, how can we just quickly draw it and turn it back into this carbonyl and alcohol form? And so for that, I have a little diagram over here. So for an acetal, the way I think about the fake mechanism going backwards is we need to locate the carbon that has the 2 ORs on it. We need to cut both of those carbon OR bonds with that central carbon. And then when we erase those bonds, it looks like this. It's kind of freewheeling. And then what we do is at the central carbon, we plop on a carbonyl. And then with our ROs, we add hydrogens to make it a neutral alcohol. So with that in mind, let's try out a practice of that. So let's look at this one. Our step 1, we locate the central carbon, the one that's attached to 2 ORs. And here we can think about this whole thing as an OR, this is an OR, and they're both attached to this carbon. So that's our kind of central central carbon. Then we are going to cut these 2 bonds between the oxygens in the OR group and that central carbon. So for a minute, I'm going to write it as if I've cut all those bonds. And now, in the fake mechanism, what I do is on the carbon that was our central carbon, I put on a carbonyl. And then on the floating O's, I add hydrogens to make them neutral alcohols. And with that, we've successfully disconnected. We have a tool now where if we see an acetal, we have a kind of regimented formula for how can we write the carbonyl and alcohol that comprise it. So let's put that into action over here. If we have an acetal and we have H3O+, the only reaction we can do is acetal hydrolysis. So let's do that process and draw what our carbonyl and our alcohol should be. So first step, I locate the central carbon that's connected to 2 OR groups. Then, after I locate that, I cut the bonds between the oxygens and the carbon. So that's going to give us this on one side, and the other side I'm going to draw in those 2 hydrogens just to help us, because otherwise it looks a little weird. At the central carbon, we said that we put on a carbonyl. And then on the floating O's, we add H's and make it a neutral alcohol. Ooh. Well, I see that this molecule right here is the alcohol in our product. Great. And then it looks like somehow this formaldehyde molecule is going to turn into our hydrate. And if we think back to our hydrate formation mechanism, we know that the hydrate formation starts off with an aldehyde and like water and acid or base catalyst, and it makes a hydrate. So we are going to have kind of 2 big parts here. Part number 1 is the acetal hydrolysis. This is going to be the reverse of our acetal formation. And then part 2 is our hydrate formation in acid. So that's not totally obvious that these are the 2 reactions that we are gluing together here. And the tool that really let us start to kind of piece that together was thinking through these disconnections. And honestly, doing this disconnection, it might seem a little bit like more work at the very beginning, but it's going to save us time because now we have a target. We have like a benchmark point before the end to keep us focused. And we know every arrow in this first part is going to be our acetal hydrolysis mechanism. We know every arrow in this is going to be our hydrate formation. And so it actually, I think, makes it a little bit easier to break it down. So with that, let's kind of fly through the mechanism. So first off, we are doing the acetal hydrolysis. And so far, we haven't really talked about the hydrolysis mechanism, but it is going to be the exact opposite of the acetal formation. So acetal formation, we did these kind of 6 steps in order. And now, to do the acetal hydrolysis, we're going to do the reverse of all of these. So the final step was we had a protonated acetal that we deprotonated. So to go backwards, our first step is we need to protonate one of the oxygens in our acetal. We are just undoing the last thing that we did. So this is going to go and grab a hydrogen from H3O+. Okay. So then, let's look back before. Also, I'm like confusing myself now. No, we're good. So right before this, we had an alcohol nucleophile attacking a carbonyl electrophile. So how do we go from this to this? Well, the way that we undo a nucleophile attacking a carbonyl is a lone pair push. So we need to do a lone pair push from one of our carbons and then kick off an alcohol. And that would effectively undo what was done in this step in the formation reaction. Now, when I'm thinking about this, I'm thinking about just doing the reverse of the forward reaction. You could also just do the reverse reaction as a separate reaction in your head and like know the like 6 steps of that reverse reaction and go based on that. But here, I think that just in the interest of time, I'm going to kind of work backwards. So I'm going to lone pair push from this other OR group, and I'm going to kick off an alcohol. Okay. So now we have a free alcohol over there, and down here, I'm going to draw on the little hydrogens to make it look a little bit more normal. We have a carbonyl. Okay. So then, before this is when we kicked off water, right? If we were kind of going backwards. So to undo kicking off water, this is the point where water needs to come and attack. So the water is going to attack the carbonyl. And maybe I'll draw it as OH2 first. We've reached the point of the evening where the creepy ice cream truck is driving by in my neighborhood. So, love that for me. It's crazy because if it was not for y'all, I would vacate my house at this time to avoid it. So really, really love y'all that I'm here. It's so creepy. Okay, so now we are at this intermediate, and what came before this lone pair push that we undid with the water attacking is we had a proton transfer. And now we need to think about, okay, the proton transfer in the forward direction was in order to kick off water. But in the reverse direction, we are going to try to be kicking off this other alcohol. So, to do our reversal where we are kicking off the alcohol, we need this to be the lone pair pusher. So we need that to become neutral, and we need this to become the leaving group. So we are going to do our proton transfer where we are coupling a deprotonation and a protonation. And we've made this top one neutral, and we've made the bottom one positively charged, so it's a better leaving group. So now I'm going to do my lone pair push to kick off the alcohol. I push down to form a carbonyl. And then we have kicking off our OR group. So this is going to spit off our first product. We have this alcohol structure, or this diol structure. And then we have this protonated carbonyl over here. And that's because this still had its OH. Okay. So, if we were to fully finish out the reaction, the last thing that we would do is the reverse of the first step. The first step was we protonated a carbonyl, so we would deprotonate it. But now thinking in context, if we're going from an aldehyde to a hydrate, what's the first step of this reaction if it's acid catalyzed? I think the first step would just be we protonate the carbonyl. So if our last step of this first reaction gives us an intermediate that becomes the first step of the next one, we're not going to just unnecessarily do a deprotonation and a protonation, even though like it could happen, like protons are kind of flying on and off these molecules in an aqueous environment here. But it just makes more sense to assume that this is the structure after we've already done that first step in the standard hydrate formation reaction, which is after we protonated the carbonyl. So in the hydrate formation, after we protonate a carbonyl, the thing that happens is a water comes and attacks. And I'll actually make this a slightly different shade of blue, just to kind of show that we are in reaction number 2. So, from this, we have our 2 hydrogens that were already on there. We have our OH that was the carbonyl. And then we have the OH2, water, that just attacked. And now that oxygen has 3 bonds. And so we are going to need to do a deprotonation. So I just take a water that's around in our solution, and it is going to do this final deprotonation, and that gets us to our hydrate molecule. And that is equivalent to this bad boy, because remember, we don't have to draw the hydrogens. Woof! Like, again, it's a lot. Part of it, why it's a lot, is these reactions are now very long. But also, it's requiring us think a little bit more and piece together different reactions that we know now. So questions on this one? I'll ask y'all a question. Could I say, hey, I don't want to write this. I'm going to do proton transfer. And then be done. Would that work? This isn't a curved arrow. I'm just like crossing it out. Jamie, a definitive no. Why?
My thought process was like you didn't put the hydrogen anywhere else.
Exactly.
Like you had one spot and you didn't put it anywhere else. So.
Thank you. Thank you. So if you're doing a proton transfer, it specifically has to be one protonation and one deprotonation. It can't be just one protonation, nothing else, or one deprotonation, something else. It also can't be three things at once. So again, proton transfer is a very specific abbreviation that we are letting all use. My intro orgo class, we weren't allowed to use proton transfer, and my gosh, it increased misanthropy, negative emotions. It made the world a darker place. So, with great power of the proton transfer comes great responsibility. Okay, we spent a lot of time on acetals. I'm not going to spend nearly as much time on amines, enamines because it's a really similar idea. But I really wanted to make sure that we kind of touched this, we understood this reaction kind of backwards and forwards, and saw ways that's going to come up in our mechanisms. So, up next, we have amines and enamines. So, previously, we have seen carbonyls, a C double bond O, and another one that y'all probably have not seen directly, but I'm wondering if it can make sense to y'all. This is a functional group that's a compound functional group, quote, 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 called an enol. And it's made up of an alkene and an alcohol. Enol. Ding dong. Now, the reason why we consider this a compound functional group as one thing instead of an alkene and an alcohol, we don't consider them two separate functional groups because there is resonance. All of these have p orbitals on it, they're delocalizing, and so this thing reacts as one group. It doesn't react as two separate groups. You're going to see her probably in lecture 10. She's going to come back. But the reason why I'm putting her here is because now we have the nitrogen flavors of these guys. So, the nitrogen version of a carbonyl we call an imine with an I, imine. And then the nitrogen version of an enol we call an enamine. And again, enamine, oh my gosh, we love a portmanteau. And again, it reacts as one functional group. If you were to circle this and call this an amine and an alkene, that would be wrong. Because they don't react like a normal alkene or a normal amine, this thing has resonance, so it's reacting as one group. We also have some side players in the game. So if we protonate an imine, it's called an iminium. And then if we have something that's halfway to an imine, we call it a hemiaminal. My favorite story about this is my first Harvard organic chemistry class that I was in. I remember being in the lecture where this was taught, or actually it was section, and the TF just nonchalantly said, and then we form our hemiaminal. And my gut response to hearing that was, Gesundheit, that sounds like an involuntary utterance. That's not real. What games are we playing out here? This is fake make-believe land. Y'all are having too much fun. A hemiaminal, sure. Sure, Jan. Other kind of nomenclature things that we should introduce here are, we have the notion of a primary amine and a secondary amine. So we classify amines as either primary or secondary based on how many carbons are attached to the nitrogen. So here, this nitrogen's attached to one carbon, we call it a primary amine. This nitrogen's attached to two carbons, so it's called a secondary amine. This one, tertiary amine, and so on. I want to really quickly contrast this to alcohols. So when you talked about classifying alcohols are only ever attached to one carbon, right? We're never really going to have an alcohol attached to two carbons, then it would be like an ether. And so here, we call these primary and secondary based on the carbon. This carbon is attached to two other carbons, it's a secondary carbon. This one is attached to one other carbon, it's a primary carbon. But that convention is different for amines. For amines, it's about how many carbons are connected to the nitrogen. It does not matter the classification of those carbons. So like this is a primary amine, so is this, so is this, because in each case there is only one carbon attached to the nitrogen. The last thing, and I promise I will be done with the nomenclature soup, is I'd like to just very briefly introduce this notation of alpha and beta. So if we have a carbonyl or an imine, the position right next to it we call the alpha position. And then the one away from that we call the beta position. And I promise it's going to come back and we're going to talk about it. But here we can call the hydrogens on this alpha position alpha hydrogens. We can call the hydrogens on this beta position beta hydrogens. And as we get into the next few lectures, we're going to start to see reactions that involve alpha positions and beta positions. So it's something that's coming. You're definitely not going to be tested on this, so don't freak out with it. But like, there's definitely a step that's going to happen in our reaction where it's helpful to use these terminology just so we can give it a name. Because otherwise it's just like, then we do that thing, rather than specifically naming something like protonate the carbonyl, blah, blah, blah. So, when we are forming amines and enamines, the setup is really similar to alcohols and forming acetals. So, when we formed an acetal, we used an alcohol and we used acid. Here, when we are forming amines and enamines, we are going to use our amine, and then we are also going to use pH of about 5. This is mildly acidic, but very mild. And so Serenia went into some detail in this in the lecture notes of why we need these mild conditions. But the thing that you should know, the important part, it is not acidic enough to protonate a carbonyl. So your first step of these reactions will not be protonating a carbonyl because it's not acidic enough to do that. Okay. So the essential idea that you should get from these line reactions, though, is if you react your ketone or aldehyde with a primary amine, you are going to get an imine. If you react with a secondary amine, you're going to get out an enamine. And so it's important to clock what type of amine you're reacting with, because that will determine what the end product is, if it's going to be the imine or the enamine. And just like you memorize functional groups for the first exam, I would commit these functional group names to memory, because otherwise it's really going to be hard to talk about this, like you won't have the language for it. So the steps of this are really, really darn similar to what we've seen before, but we said that the first step here is not going to be protonating the carbonyl. We're not acidic enough. We're not an H3O+. So our first step is our amine is just going to go and attack the carbonyl. Now, why can an amine just go and attack a carbonyl, but an alcohol can't? Like, why do we need a strong acid for an alcohol, but for an amine, we don't? Let's look at the homos in these. So up here, the homo is a lone pair on oxygen. Down here, the lone pair is a lone pair on nitrogen. From our MO theory, do we remember which one of these is higher in energy? A lone pair on oxygen or nitrogen? What is higher in energy?
Nitrogen.
Nitrogen. And that's from our low energy trifecta. We said things that were more electronegative are lower in energy. Oxygen's more electronegative, so this lone pair is lower in energy. And remember, for homos, for donors, we want it to be as high energy as possible in order to lower that homo-LUMO gap. So, because we have a better lone pair on nitrogen as our homo, we can just go and straight up attack the carbonyl. So that's step 1. We attack the carbonyl. Step 2, and this is where I did something a little bit different than Serenia, but I think we're both right. Like, I think they're both totally fine and valid. So in Serenia's version, she first did a protonation of this with whatever is in the solution. Like, I think that she used, like, let me double check exactly what she used. Yeah, she used an H3O+. She protonated this first, and then she did a proton transfer. And looking at it, we need to get from this starting point to this ending point. And so let's keep track of our hydrogens. We need to do 1 deprotonation here, and then we need to do 2 protonations over here. So no matter how you cut it, getting from this first point to this point, you need to do 2 protonations, 1 deprotonation. And another way to say that is you need to do 1 protonation plus a proton transfer. Because remember, we can abbreviate a protonation and a deprotonation as a proton transfer. The way I show mine is doing a proton transfer first, and then I'm erasing this hydrogen, I'm adding on a hydrogen here. And this takes us to our neutral hemiaminal intermediate. And then afterwards, I still need to do a protonation. So I would go and grab a hydrogen from, in this case, we would do OH2 in a reaction. I guess I can leave that red arrow there. So that's how I did it. The way Serenia did it was she protonated this. And then once she was at the OH and NH are 2 plus, then she did a proton transfer and then got to here. Both are totally valid. Like, both are accurately using a proton transfer abbreviation, so it does not matter which one that you do. The reason I like doing mine this way is because I like showing this hemiaminal dude just because I like the name. Also, it's the neutral intermediate, so it's going to be the species of the intermediates that you see most common in the reaction mixture of the intermediates. So once we get to this state, the whole reason why we did this, remember, we are trying to kick off a water. So here, we had an oxygen in our original. We do not have oxygen in the products. And so just like in the acetal reaction, we packed her bags and kicked her out. And water is kicked off here in this step. So we do a lone pair push from the nitrogen, kick off water. And then we are at our aminium. So questions on the first steps here before I talk about this final last step. That's a little bit different depending on if we had a primary or secondary amine. Another side question, are y'all seeing parallels between this reaction and the acetal reaction? Or do these just feel totally different to y'all? It's totally okay to be these feel like totally different things. Maybe one thing I will kind of point out is both of these reactions, we refer to them as addition eliminations. So in this reaction, we have added on something, and we've also kicked off something. We've kicked off a water from this oxygen. In the acetal reaction, we added 2 OETs, and again, we kicked off a water. We eliminated a water, addition and elimination. In all of the reactions that we did in lecture 4, for these reversible additions, all of these were just addition. We didn't kick off anything. We've just added something onto the molecule. And then in all of our CAD reactions, we did substitutions and we reformed a carbonyl. So, again, lectures 4, 5, and 6 are all about carbonyl reactions. But here, we just did additions for lecture 4. For lecture 5, we added and kicked off something and reformed a carbonyl because we are at the CAD level. And then for lecture 6, we did addition eliminations where we fully have kicked off a water as part of our reaction. So last step, I won't belabor it anymore, is I just did an abbreviation here of this amine where this amine, if I do it as 2 R's, imagine they could be 2 carbons, it's a secondary amine to start. Or I could have done one with an R and another H on it, so a single R. And all of the steps, no matter which one we do, primary or secondary amine, are the same. all the way up until we get to the iminium. But then, let's see how these would be different if we started off with a primary amine versus a secondary amine. So if we start off with a primary amine, at this point, we only have one bond to a carbon, and we have one bond to a hydrogen. The thing that we need to do is just to neutralize the molecule, because we don't want to have a final product that has a positive charge. And so, something in our solution, I think that Serenia for this uses water. Let me double check. Yeah, she uses water. See, in my version that I'm used to teaching, we didn't care about what the identity of the thing that does the protonation or deprotonation is. And so we just let students use sol for like solvent. But that's not for this class. So water came and just deprotonated it, made it neutral. Easy peasy. The issue is when we have a secondary amine, both of these bonds are carbon-nitrogen bonds, which are pretty hard to break. So, because we do not have an easy way of deprotonating the nitrogen here, what we do is this sneaky move that's called an alpha deprotonation. So, what happens is a water molecule is going to go down. We said we have our imine, and the position right next to it we call the alpha position. So, a water is going to come and remove one of the hydrogens at the alpha position. The electrons in the sigma CH bond are going to push towards the nitrogen, towards the carbon, I guess, first, and then we push all the way up to the nitrogen. And it's a way of giving electrons to the nitrogen to make it neutral while removing one of the only hydrogens that we can actually remove. Because otherwise, we would be left with trapped in a positive charge on the molecule. So this last step is really the only difference between the two versions of the primary amine version or the secondary amine version. And it controls whether we end up with an imine or we go all the way to an enamine for our product. So that's the forward reaction. I'm not going to do a beat by beat of the reverse reaction, but the reverse reaction, literally the first step is different, and then the rest of the steps are the same because you are literally undoing the exact same things that you did before. The reagent that you use to undo these is H3O+. And just like we did with acetal reactions, you're going to want to practice a fake mechanism for like, how could I go from an imine and write the ketone aldehyde and amine that came from it? So like, for example, I would want to cut this bond, put a carbonyl on one side, and put two hydrogens on the other side. And that would get us back to this. So the same process that you use to study the acetal, you will use for this to practice and build those skills. So with that in mind, let's look at practice number 2 here. Great, I hate it. First step, panic. Second step, identify functional groups. What functional groups do we have in the starting boy? Alcohol, great. Ketone, great. Amine, wow. Jamie. I was going to say like hot off the presses or something being like Speed Demon. Speed Demon Jamie, reporting for Dooney. The other thing that we have is pH 5, which pH 5, an amine and a ketone, these are giving classic amine-enamine conditions, right? Like anytime you see pH 5, the first thing that you should be thinking is like amine formation or enamine. Now, what type of amine do we have here? Is this a primary amine or a secondary amine? Well, we ask ourselves how many bonds to carbon does the nitrogen have? It only has one. So this is a primary amine. So we know that this is going to form an imine. Okay. Now, we also have some other things over here. So if I put an alcohol, a ketone, and let's say I had a stronger acid. Let's say I had H3O+. then what would you think, reaction-wise, could we do with this? If we had an alcohol, a ketone, H3O+. Is that a reaction you've seen before? An alcohol and a ketone combining with acid. I mean, it couldn't be the reaction we just spent an hour on. Could it? Could it? Yeah, like acetal formation or hemiacetal or something in that family. So we could imagine potentially starting off with like acetal. So why do we know it's imine? There are kind of two factors. Factor number one, the lone pair of nitrogen is a better donor than lone pair of oxygen. So we know that this is just going to attack first. And then second, we're not acidic enough to protonate the carbonyl. So we are going to be doing some sort of imine formation. And just like we did with the last mechanism, I think it would be really, really helpful for us to just draw what the imine's going to look like. So, using our line reaction level to give us a target of where we're headed, in order to go from a ketone aldehyde and a primary amine to an imine, what we need to do is erase the carbonyl, and then we need to put a double bond to the NR and erase the hydrogens. Do you buy that as a fake mechanism for just like how we can draw the product from the starting material? We erase the carbonyl, we put a double bond to a nitrogen, and that nitrogen has this R group on it, and it looks like we've just erased the hydrogens. Okay, let's try it. So, first things first, I'm going to erase the carbonyl, but this is where it was. I'm going to put a dot there to save the spot. And then I need to essentially connect these two with a double bond and erase the hydrogens. Whew, boy, that looks bad. Let me see if I can clean it up. This is going to form a 1, 2, 3, 4, 5, 6-membered ring. So what I'm going to do is I'm going to just draw a 6-membered ring. I'm going to put a nitrogen as one member. And then I'm going to put the double bond here. So like this is carbon 6, and then 5, 4, 3, 2, 1. Okay. And actually I hate how I've drawn the numbers, so I'm going to clean it up really quick. So I call this nitrogen 1, 2, 3, 4, 5. And then this was 6. And then we know that off of 6, we need to have the dangly bit with the oxygen. Okay. Well, interesting. So, yeah, no, I think that works, right? So it's kind of weird because it's intramolecular, it makes a ring, but we've done the things we need to do. We erased the ketone completely. We made a double bond to the N, and that N is attached to 1, 2, 3, 4 carbons. 1, 2, 3, 4 before we get to the carbonyl or the amine position. So I'm going to erase this just because it looks horrible and say, okay, this is our first like benchmark point. This is what we need to try to get to. This is our amine. And then trying to look at, like, going from here to here, we can do by verbatim copying the curved arrows from our lecture notes or section notes. So that's going to be fine. How do we get from this bad boy over here? Well, it looks like this oxygen needs to come and attach over here. And does that form a 5-membered ring? 1, 2, 3, 4, 5. It does. And we know amines, just like carbonyls, are electrophiles, right? So what happens is we're going to have, once we form this, the OH attacking the imine, and then maybe we have like a deprotonation or something, and then we should be done. So that's kind of our two parts. We first form the imine, and then we interact with this OH in the imine. And this is the part where, like, this step, we have never shown you. That is the one new thing. But do you see how we convinced ourselves that this has to be what happens? Because we somehow need to have an O bond to this carbon based on our product. It forms a 5-membered ring. And we know that if we have these conditions, we are going to form an imine. So based on that, we've kind of like trapped ourselves into, I know we've never seen this before, but that must be what happens because we just don't have any other options, and that's the only thing that makes chemical sense. And so one thing I want to like be clear is, like, when we are trapped into this option, it is after exhausting all the reactions we've seen. Whereas I think I see on some problem sets before people are like clocking that a lot of them are really heavily based on a reaction you've already been taught, people try to do new moves early. And I'm like, no. You have to exhaust everything and be forced into a corner before you do a new move. But without further ado, I'm going to kind of fly through this mechanism because we aren't going to have time to do everything else, but I want to at least talk about it before 7:30 when office hours hits. And then I'll finish recording the section video to include some more information talking about the last little bits. So I am going to go off to the races. Maybe I'll time myself, see how fast can I draw the imine mechanism. Lone pair attacks the carbonyl. Love to see it. Remember, it attacks directly because we are not acidic enough to protonate. So I'm drawing this kind of weird. I'm drawing it in a way that's really suggestive of the products. And you can always number these 1, 2, 3, 4, 5, 6 to confirm 1, 2, 3, 4, 5, 6 that we did have a direct correspondence here. So when we attack, we first make this intermediate, which has a plus and a minus charge right next to each other, which is called a Zwitter ion. And then this is where I normally do my proton transfer. So now I've made it totally neutral. We are at the hemiaminal now. And the thing that we want to do is we want to kick off the OH as water. So I'm going to do my second protonation. So now I have my good leaving group. And now the drama, the cinematic moment, the lone pair push. We're going to push down from our nitrogen, kick off the H2O water. Okay. So now our nitrogen over here has a positive charge. And the last step of the imine formation mechanism would be for us to deprotonate this. But let's pause for a minute, just like we did in the last one. And the first step, like, I guess we could deprotonate this and have an alcohol attack. Or we could just have the alcohol attack the protonated imine. Which is going to be better? Option 1 down here, the alcohol to attack this protonated imine called an iminium. Or 2, to deprotonate, then have the alcohol attack a neutral imine. Which one has the better electrophile? What's going to be the better electrophile? And
The positive charged.
yeah, because a protonated imine is kind of like a protonated carbonyl. It's a better electrophile. Its LUMO is lower in energy. So if you could attack straight up the iminium, and that's going to be the better electrophile, why would you go and form the neutral version that's a worse electrophile and then react? Well, you wouldn't. And especially since this is an intramolecular reaction, meaning it's all happening within the same molecule, it's just going to be faster for this to go and attack at this point. And this is where I'll switch to the second color for the second part of the reaction. So now I've made a 5-membered ring onto this. I'm going to draw it very suggestively to look like our product. You can always use your intermediate that you've drawn or the product to kind of help you suggestively draw atoms in the right spot of where it's going to go. Now, you can't use it to like magically poof away bonds or anything. So like when we attacked with this OH, like what I've drawn so far is the product. But remember that oxygen still had an H on it at this intermediate. So we are so close to the product. Our last step, we have to do a deprotonation here. And that will take us all the way there. So I know I did that rather quickly, but all of these curved arrows in blue, straight up verbatim copying from the lecture or section notes. Again, the challenge is going to be seeing what we should do rather than like, or I guess what should not be the challenge is memorizing the steps. Like that's something that we have to do. And that's part of what makes it hard. Like being able to bang out an amine mechanism once you've clocked that it is an amine reaction is a skill that you will need to work on. That is a specific type of studying for memorizing, like what are the steps of the amine reaction, knowing why it happens. And that skill is completely separate from this first skill of figuring out what reactions are happening. And when you are like doing your problem set and doing your practice problems, you need to be working on both skills. Like if you know all of these reactions from lecture cold, but you haven't really practiced identifying which reactions are happening and why, then you're going to be screwed on the exam because you have all your reactions, but you're just not going to be able to connect it to problems, new problems. And then if you only practice this, you might be able to figure out what the idea is, but you won't be able to kind of do the full curved arrow mechanism working it out. So really there are two things in tandem. I've had a few students email me like asking about like studying reactions and memorization versus not memorization. It's both. There are some pieces of information like the reaction mechanism that you need to have memorized and on lock. And there are some things where you need to be forming these skills where you're thinking through which reaction might happen and why. And that's not a memorization. That is a like getting to know how molecules react thing. And again, like my first reaction when seeing any problem, like even this one, was just like gross. And yet we have our tools of analyzing functional groups and matching everything. Last thing I want to talk about very, very quickly is protecting groups. I know that we are at 7:30. I'm going to take 5 minutes because I think protecting groups are important and I think that they're challenging. If you need to pop off, that's totally fine. By pop off, I meant like exit, not pop off like angry. And then in the video, I'll kind of talk through some of this for the practice. But let's say we want to go from this starting material and form each of these products. So one thing I'm noticing when I look at this is we have carbonyls over here. And over here we have like some alcohols. So if we're going from a carbonyl level of redox, like oxidation level, to an alcohol level, are we doing an oxidation or a reduction? Reduction, great. Yeah, because we're going from oxidation level 2 and oxidation level 3 over here to oxidation level 1 and 1. So what reagent could we use to get from this starting molecule to product A?
LAH.
Yeah. So we would do lithium aluminum hydride with ether. And second step, acid workup. Great. So now slightly harder. What if we wanted to get product B, where we've only reduced the ketone, but we haven't reduced the ester? Because we know lithium aluminum hydride, toxic masculinity, it's going to react with both of these. So how do we get just B?
We need to protect the ester.
Not exactly. So, like, yes, potentially, but y'all don't know a way to protecting esters, actually. There is one reaction that we could do, like, straight shot.
Oh, the sodium.
Yeah. So sodium borohydride, remember, this is our milder conditions, NaBH4 with a methanol or like an alcohol. When we have sodium borohydride, because it is more mild, it will react with ketones or aldehydes, but it will not react with esters or any other carboxylic acid derivatives. So that's a way that we could just get one reduction, but not the other. But now, if we were to try to do this, where we reduced the ester, but not the ketone, that is harder. And this is where this idea of protecting groups comes in. We know that lithium aluminum hydride is the only way that you've learned in this class to reduce an ester. So we know that we have to use this, but we don't want it to reduce this ketone. So what we are going to do is we are going to turn our ketone into a different functional group that doesn't react with lithium hydride. So what I'm going to do as a first step is I'm going to add a diol, and I'm going to add like H plus catalyst. So if I'm having alcohols, H plus, and a ketone, well, those are the reagents for an acetal. So our fake mechanism for writing the product of an acetal reaction is we erase the carbonyl and we put two OR bonds in its place. But when we use a diol like this, both of the R groups are on the same molecule. So we have like OR and OR, and they're just connected in the middle. So it does this fancy thing of we put both oxygens here, and we know that there are two carbons in between them. Two carbons. So it makes this little 5-membered ring, acetal. So now, acetals are really not very reactive at all, especially under non-aqueous conditions. So, does lithium aluminum hydride react with an acetal? No, it doesn't. It only would react with the ester at this point. So now what we can do is we can do our lithium aluminum hydride with ether and 2 our H3O plus. Our acetal is left unreacted, and then we've reduced our ester all the way to an alcohol. And I might even do some coloring to help. So here we have just protected the ketone as an acetal, and it's protected so it's not reacting. But then the nice thing, the whole idea of strategy with protecting groups is we have a protect phase, and then we have a deprotect phase. So our last step is we're going to do acetal hydrolysis, and we are going to remove the acetal. Deprotect. And that's how we get there. So it's this really powerful idea that if we have a lot of functional groups on molecules, we might want to protect a functional group so it doesn't do some reaction. And right now, the only real way that y'all know of protecting, I think, is protecting a ketone or aldehyde as an acetal. There are other things, like you can protect a carboxylic acid as an ester, and that comes up in like amino acid formation. There are other protecting reactions that like different classes learn, but I think that this is the main one that you know right now, the main strategy here. And so we're going to keep these in mind as we do big reaction webs like this, where we have some things that we want to react and we might not want other parts of the molecule to react. So I will finish after my office hours recording a video to talk through these line reactions. And then practice 4 here is really just kind of brainstorming all the reactions you know. I'm not going to do a full, like, every reaction, but I'm just going to, like, start you off on that in the video. So hopefully that will be helpful, but thank you for bearing with me as I am sick and, like, do not have everything super polished. I'm going to try, hopefully by Thursday, to get some nice versions of these notes up, so that you have that and that you have a nice study resource. But thank you for coming to section so far, and I will go ahead and switch over to help room. Okay, folks, we're back in it. Just me. The time is now, oh my gosh, midnight. So I'm going to be brief about this. I'm going to try to go through it pretty quickly. In the video, we had just talked through what protection groups were. They were a strategy in order to not react with certain parts of molecules, where you protected it in one step. So here, typically, we're protecting ketones aldehydes as acetals. Then we can do the other reactions we want to do. And then we can deprotect it later on. So that's the kind of strategy. So now let's look at some line reactions. So again, for these, I'm going to go pretty quickly since it's just me here. When we are doing these like reactions in a scheme here, we literally are playing a spot the difference game of what has changed. Well, the difference here is we had a ketone, then we had an alcohol. So I know if we go from ketone to alcohol, we're going from oxidation level 2 to oxidation level 1. We're doing a reduction. And so for a reduction, we can use either sodium borohydride with MEOH, or we can use lithium aluminum hydride with ether in the second acid workup. Either one works. Both of them will react with ketones. So, cool. Then the next step we don't need to worry about. They just did it for us. Apparently PBr3 replaces an OH with a BR. We don't care. Then we have this, H3O+. And our two functional groups that we have are an alkyl halide and an acetal. So we don't really know any reactions of alkyl halides except for forming the Grignard or forming organolithium. So we know that this is going to be the reagents for acetal hydrolysis. So for acetal hydrolysis, we do our fake mechanism where we locate the central carbon connected to two ORs. We break the bonds to the two O's. And in its place, we put a carbonyl. The other thing is we have these for our O's, and we put H's, and that forms our alcohols that we kick off. So here I can just be like, that's a side product. We don't really care about it. So do you see how, like, all of this, we could have started off and done a protecting group. So we could have started off, or actually no, it wouldn't have worked here, so disregard me. But imagine right now, for this first one, the acetal protected a ketone, and it's protecting it, and now we are doing our kind of deprotection, where once we got through this reaction that normally would affect this ketone here, we then can remove the acetal and get back to a carbonyl that was protected on there the whole time. Okay, now I need to go from a carbonyl to an amine. So that is the one reaction that we haven't talked about yet, so I might come back to that in just a minute. Then we are going from an amine over here to an amide. So I know amine to amide, in my CAD reaction family, we make amides primarily from acid chlorides. So what I'm going to do is I'm going to cut along the amide bond from the N to the carbon with the carbonyl. And on the carbonyl side, I'm going to put a chlorine. So we have that. On the other side, we put an H and we make our amine, which that was this starting material. And the other thing that we add is we add pyridine to act as a general base in the reaction. So that's the reaction that goes from an acid chloride to an amide here. And we use an amine in pyridine. Okay. now, I think that that's the end of this path. I think that that's what this line means. But we have an alternate strategy. So it says we could do, starting from this, and then make a bunch of stuff over here. So one thing that we see is we go from our acetal to a ketone. But the other thing that we see is we go from a alkyl halide to, we've added a carbon and we have an OH. So anytime we are thinking about adding carbons, making carbon-carbon bonds, the bell that should go off in our head is Grignards. Grignards and organolithiums. That's our way of making carbon-carbon bonds. So imagine we did first step, turn this into a Grignard. Well, now we have our MGBR. We want it to attack something, and specifically we want it to attack one carbon in a carbonyl. So if we have one carbon in a carbonyl, well, this carbon has two hydrogens on it, right? So we want it to attack this molecule in order to have this carbon at the base become the star at the bottom, and then I'll move this a little bit so you can see it a little bit better. The actual mechanism. We would attack the carbon and then push up, and it would make O-. So we are attacking this formaldehyde in ether. Both of these need to happen in ether. And then that will take us to a version where we have O- here added, and we've added our star carbon. And then we still have over here the acetal. So now we need to do the workup from the Grignard, which is H3O+. But H3O+ is also what we use to remove an acetal. So H3O+ is going to protonate over here, make that OH, and it's going to turn this into the carbonyl version. So doing our acetal hydrolysis. So that accomplishes a lot in one step. So how do we know that we did it in this order? Why did we not do the acetal hydrolysis first? Well, if we did the acetal hydrolysis first and made this into a carbonyl, well then when we go to make our Grignard, MGBR, this would just go and attack another equivalent of the carbonyl. So like it would just go and attack, bloop, down here for another like molecule, and essentially it would all react with itself, and it wouldn't attack formaldehyde. So that's why, again, this idea of having a protecting group that doesn't react is going to be important and helpful for us. So that is these three steps here to go and form this intermediate. And then we have chromium trioxide and H2O. So remember, H2O as the sidekick takes all the way to a carboxylic acid. So, and that only is really applicable to a primary alcohol or an aldehyde. Because you don't know the mechanism for it, but the core idea of it is this chromium kind of gobbles up a hydrogen at the carbon. So here, a ketone, we don't have a hydrogen there, so there's nothing to gobble up. But over here, this primary alcohol, we have two hydrogens we can gobble up, so we can oxidize it to oxidation levels. So that's going to take this carbon and make it into a carboxylic acid. And we are done there. Okay, now moving on to our last section. One other strategy, kind of like protecting groups, that combines a few different things, is a process called reductive amination. So let's recall our reducing agents. Previously, we've seen lithium aluminum hydride, which this was I nicknamed toxic masculinity. Super reactive. It reacts with everything. Ketones, aldehydes, esters, other CADs. Like, it is the most reactive. Because of that, we have to do like step 1, the lithium aluminum hydride and ether. We do step 2, H3O+. So we can't do it in an aqueous environment. Then we had NABH4, our soft boy, only reacting with ketones and aldehydes, does not react with esters and other CADs. It's not strong enough for that. So this one was the one where we could do with like MEOH and do aqueous environment. But now, let's introduce a third reducing agent into the mix, NABH3CN, which I typically call softer boy. So, whereas here, lithium hydride, everything, NABH4, only ketones and aldehydes, NABH3CN will only react with good electrophiles that are like positively charged. So, it's going to react with aminiums, so nitrogens in a CN double bond with a positive charge, or protonated carbonyls. And there are other circumstances where NABH3CN can react. They can react in something called conjugate addition, which you'll probably see later on in the course, so don't need to worry about now. But for now, you need to know that, okay, it's an even weaker nucleophile, and it's because the CN is going to withdraw inductively. And so, because it's even weaker, it's not going to react, namely, with a ketone or an aldehyde. Also, one thing I should mention here, if these will react with aminiums, then one thing that we should know is that actually lithium hydride and sodium borohydride are going to react with imines. So we could reduce an imine with these reducing agents and take it to an amine. And again, I don't think that was explicitly shown anywhere, but it's going to be a better, or not as good, like, it's kind of anything that's below here in terms of the electrophile strength, everything stronger as a reducing agent will react with. So lithium hydride would react with this. Sodium borohydride would react with this. NABH4CN would react with this. The big difference is these are also, like, especially lithium hydride is a really strong base. And so if you were trying to get this to react with a protonated carbonyl, really all it's going to do is deprotonate the carbonyl. So it doesn't do the nucleophilic attack that we want. So maybe the easier way to do it is to think about the functional groups it does react with, where lithium hydride will react with all of our main functional groups with like carbonyls. It will even react with like a nitrile. We saw that. Sodium borohydride reacts with ketones and aldehydes. I believe in also amines, but I don't think that we saw that specifically anywhere. I think that this one will also react with amines, but I don't think that you saw a version of that in lecture. But yeah, I'm just kind of saying it now. Sorry, it is very late. And then this new character, NABH3CN, will only react with those aminiums, protonated carbonyls, like really, really good electrophiles. So, the strategy is we want to have a new way of making an amine, which we know amines are at oxidation level number 1, and ketones aldehydes are at oxidation level number 2. So we both want to make an amine and we want to reduce it. And so our strategy is, first, we are going to use our aminium formation reaction, the full reaction that we've already seen, turn it into an aminium, and then we're going to use this new softer boy to reduce our aminium down to an amine. And so overall, we call this process reductive amination. It's an amination because we make an amine, and then it's reductive because we go from oxidation level 2 to oxidation level 1. Okay, so what that looks like is, remember, softer boy, just like NABH4, can be in aqueous conditions. So we can keep it with the pH 5 and with the amine here. And when we put all of these together, it looks like we are going to be replacing the carbonyl with our amine. And then the other thing that we've added onto the carbonyl site that we didn't write out is a hydrogen. And that's from our reduction from this NABH3CN. So the mechanism for it is, first you do the entire amine formation mechanism. This is like straight up this whole mechanism, blah, 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 here. And then the only difference between this and if we did not have NABH3CN, all you would do in the last step is water would come and deprotonate this, you'd be done, you'd be an amine. But now that you have this, and this does react with protonated carbonyls and protonated amines, so aminiums, now for the last step, the sigma BH bond is going to come and attack here, and that's going to add this hydrogen and reduce all the way to an amine. So, classic signs are, if you see this reagent, NABH3CN, you know you're doing a reductive amination. That's the only way that you've seen it before. The other classic sign is if you have formed an amine, there are only a few ways that you know how to form an amine, and we'll talk about those in a minute. But forming an amine from like a ketone or aldehyde, that's the other tip-off of, okay, I need to introduce a nitrogen and I need to reduce reductive amination. So let's look back at this. Here we have a ketone going to an amine. Okay, we need to introduce a nitrogen and we need to go down an oxidation level from oxidation level 2 to oxidation level 1. So in that, we're thinking reductive amination. So to see what our amine is, we know that we have pH 5. We know we have NABH3CN. But then to figure out what our amine is over here, we need to cut where it was added. Okay, so our amine had to have this nitrogen and it had to have the CH3. And then we just want to add hydrogens to make it neutral. So this will be neutral with NH2. So our amine is going to be MENH2. And that's how we would form this amine via reductive amination. So the kind of last thing I want to end it off on is practice number 4 is doing a reaction brainstorm. So what it does is it divides up functional groups by oxidation level, because that's our big kind of grouping of all of these. Oxidation level 3, 2, and 1. And then it's asking us, okay, if we have all of these functional groups, what are all the reactions that we know how to move between them? So, for example, let's say I start off with an amine. And I can imagine two different ways an amine looks. One way an amine looks is with an NH2, and the other way an amine looks is with some alkyl group on it. Now remember, it's never going to have another alkyl group on here because then it's going to be locked with a positive charge, and it would then go on and form an enamine instead. So, if it's an amine, we're one of these two options. And then we could reduce an amine with like lithium aluminum hydride here, and that would form, let's see, if we reduce it, we are going to be adding a hydrogen here, making this a single bond. So now this nitrogen is attached to 1, 2 carbons. So that would form a secondary amine. So that would be with lithium aluminum hydride in ether and 2 H3O+. And again, I think sodium borohydride would also reduce that, but y'all haven't really talked a lot about this explicitly. Similarly, over here, this one, if we reduced it and added a hydrogen there, then that's now a nitrogen that's only attached to 1 carbon. So that's a primary amine. So bloop. And we could do the, I'm just going to call this, quote, LAH. And LAH is my abbreviation for this. On exams, you do want to write lithium aluminum hydride ether step 1 and step 2 H3O+. But just because we're going to be doing a lot of these and they're the same reagents, I'm just going to write LAH. Okay. Then if we have an enamine, we know that we're going to have an alkene, a nitrogen, And the nitrogen's going to have 2 other R groups on it. So we don't really have a straightforward way of reducing this down to just an amine. Like, we can do a hydrolysis, and maybe that's another thing that we can think about. So here, these are reductions, lithium hydride, but we could also just sever this, right? So we could go from this imine, and if we just add H3O+, then that is going to sever this, make NH2, and then put a carbonyl on it. So we can make a primary amine that way by chopping up an amine. And then over here, we can hydrolyze an enamine, and that's going to chop it up down here and then make our carbonyl, and that would make a secondary amine. So we can do H3O+ to form a secondary amine. But then we have our CAD reductions. So with an amide, it depends on what our starting material looks like. So if our starting material amide had NH2 on it, then when we reduce the amide, we're essentially just erasing the carbonyl. So now this nitrogen has 1 carbon attached to it, so it's a primary amine. So we can form a primary amine with lithium hydride. Over here, if we erase this carbonyl, that's going to make a secondary amine. So we can do that with lithium hydride. And then over here, this could make a tertiary amine with our lithium hydride conditions. Woof. Then we also have that we could reduce a nitrile, and we only have one way of reducing a nitrile with lithium hydride, and that is going to necessarily make this an NH2, and we add H2 over here. So what it looks like is actually this, a primary amine. So we can't make a secondary amine from anything else. Now that I'm looking at it, I feel a little bit weird that I'm telling you that lithium hydride can reduce amines. I feel pretty confident in that, but because it was not directly covered in lecture, I'm going to gray this one out just to be really safe. Because again, I think it's just late and I'm tired. Cool. So all these ones in blue are ones that you've seen ways of making amines. But now we can also make amines from reductive aminations. So imagine we had a ketone over here. Well, we can add some RNH2 with NABH3CN at pH of about 5. And again, that's going to make single bond here to NRH. So that would make a secondary amine. So let me put this arrow to the right spot. So this would make a secondary amine. And that's if we reacted it with a primary amine. But we can also use this to make bloop, a tertiary amine if we use R2 NH with NABH3 CN and pH of around 5. Here, then we would be creating nitrogen and we would have our 2 R's on it. So now this nitrogen is a tertiary amine. It has 3 bonds to carbon. So again, yet more ways of reacting. And we could do the same thing from an aldehyde. And aldehyde, again, we are going to be able to go to secondary amine and tertiary amine. We aren't going to be able to form primary amines from it. But woof, already it's a pretty complicated web. And so I think, again, it's really, really helpful to me to think in terms of the columns of oxidation levels. And we know if we are moving at all between columns, we are doing redox. If we're going this way, we're doing reductions. If we're going this way, we're doing oxidations. And then it's about thinking through based on the specifics of the molecule. We could start off with, again, all these different versions of amides, all these different versions of amines. we can get different starting materials in terms of primary, secondary, or tertiary. Now, we could do a much more simplified version of this web. This web is like really complicated here. If we didn't distinguish between primary, secondary, and tertiary amines. In that case, we could just say like amine, and we could have ketones and aldehydes forming amines. We can have amines forming amines. We got enamines. We can have amides, and we can have nitriles. So if this is super intimidating and like you don't feel super comfortable writing out all of them, maybe a kind of starter step would just be don't distinguish between the alcohols and amines, like the different classifications. Just try to see, okay, what are all my reactions that make amines? What are all the reactions that make alcohols, and so on. And then you can do the reverse. So you can do all the reactions that start with amines and form amines and form amides and form, I think those are the only two that we can form from the primary amine. But yes, I'm not going to do all of them here. I think a key might be posted at some point for this that like does as many as we can list, or that we can think. But I also think it's going to look crazy with all of them on there. But this is the exact type of like exam preparation I would start doing to get all of those reactions really fluid and get to where you can work easily with them, and also where you can like quickly brainstorm. I'm gonna say one more thing because I'm already at 2 hours, so I'm gonna go over. Another way I like doing these that I think is a little bit more manageable is a single reaction web. So starting off with something like a carbonyl or a ketone and saying, what are all the reactions I can do from this? Well, I could use like sodium borohydride and I could turn that into an alcohol. I could do the reductive amination or something and do like NRH, and that's alcohol, that's an amine. I could do HOR and H plus, and I could make an acetal. I could do H2O and H plus catalyst, and I could make a hydrate. I could add NaCN in water, and I could make a cyanohydrin. And then I think that this is also a little bit more managed to be like, okay, here's my like hub and like destinations here for like what are all the things I can do from ketone. And then you can do another one of this of like what are all of the reactions that form ketones. And I think that that will kind of get you more on your way. The whole purpose of all this is not to make sure that you have every reaction ever and to like think through all the possibilities. It's really just to get you to start organizing and getting these kind of fresh in your head, gearing up for the test. So I think that's all I have for you. I hope that was helpful kind of going through this. Again, I'm going to try in the next day or two to clean up my section notes a little bit more and get something posted. So hopefully that will be there and be helpful. But yes, have a good day, week, evening, whenever you are watching this. Goodbye.